In today's action video, we're going to be talking mainly about phase spread amongst the different frequencies used in this multi-frequency exam. This is for a bobbin probe inside of a tubing calibration standard. What we're looking at on the left strip charts over here, left one is a channel 1 vertical. If you look on the bottom of the strip chart, you can see a deflection that goes down and back and up and back. So that's basically down and to the right on this particular signal. So I move below it with the cursor and then slowly go up into it. It starts down and to the right. Down and to the right, goes up and then back to null as the coil pair moves past the flaw. So when you look at the vertical strip chart, negative is on the left, positive is on the right. So you can see it goes down and to the left first, and then up and to the right. Okay, if we move up a little bit more, then you've got your 60% flat bottom hole on the OD of the tube. Now there's a little bit more phase there because it takes eddy currents time to penetrate through the material. Time is analogous to phase, they mean the same thing. And the display signal that you see here, what those represent are the timing of the eddy currents in the material that are disturbed. Eddy currents are swirling at every depth, provided you're using, the right frequency ranges. And the signal that gets returned is the weighted average of all of the eddy currents from every depth. Some are disturbed, some aren't. But somehow between the coil and the wire that leads up to your instrument and all of your signal processing circuits and your output, the end result is the signal that you see. Exactly how all that works, I don't know. Maybe even the best instrument designer couldn't tell you exactly how that all works, but we know there's a correlation between disturbed eddy currents at depth and the signals that are displayed. And when we compare those to metallurgical known defect measurements, we have figured out over time that, hey, these signals have some definite correlation to known metallurgical depth, and that's why eddy current testing is useful. So what we do is we calibrate our 100% hole signal, which is right here. We set it to 40 degrees because what they have figured out in the early days, Clyde Denton from Z-Tech had a lot to do with this. They could set it at 90 degrees, they could set it at 140, they could set it to 0, or if they set it to 40 degrees, what they figured out early was that ID flaws, which you probably saw fewer of back in the days, would land between 0 degrees and 40 degrees, or a fairly small phase window. And OD flaws, which you probably saw more of, would occur from 40 degrees all the way over to about 180 degrees. Now notice the reference point for zeros flip-flopped from your normal studies in math and science. Why was that flipped? There's a few stories out there why, but I actually called Clyde Denton on this one, and he said, you know what? He said, because I'm the boss, and that's the way I wanted it. So there you go. 0 degrees is on the left, not the right on most eddy current instruments. Okay, phase lag, 100%, set to 40 degrees. That doesn't mean that a through-wall defect is always going to be exactly at 40 degrees. Could be 35, could be 45. But the general theory is that if you set your through-wall hole to 40 degrees and you have a big signal that comes up to 40 degrees, you may want to investigate that as being a potentially true defect. Now, just because it's a through-wall hole doesn't mean it needs to have a very large amplitude like this. What if it was a pinhole 40 degrees? Well, all of your eddy currents at every depth would be affected because it's a through-wall hole, but the size or amplitude of your signal is directly related to the volume of metal that's missing. So if you have a pinhole 100%er, it may be similar phase to this 0.052 inch diameter hole, but the amplitude may be much, much smaller. So you can have a pinhole leak and not have a huge eddy current signal. It's all related to the volume of the metal missing. Okay, so we got 160, 20. The reason that you have more phase angle or phase lag on the 60s because it takes the eddy currents longer to penetrate down to that depth on higher frequencies. It takes even longer for those disturbed eddy currents leading up to the 20% to be disturbed. So now, if you got a bobbin ID probe and you're using 400 kilohertz, from the inside surface of the tube down to where the bottom of the 20% flat bottom hole is on the OD, that is the defective or the flawed material from the 20%er closest to the test coils, all the way down to that depth, the eddy currents aren't disturbed, but they start getting disturbed at the bottom of that flat bottom hole from the OD. So your instrument is smart enough to know that, 80% of the way through the tube wall, none of the eddy currents were disturbed, but when it got to that flat bottom hole drilling from the OD, the rest of them were disturbed. And it will give you a signal result that represents that. So that's a lot of word salad there, but bottom line is when you calibrate and you put your 100% signal to 40 degrees and you see your 60% come in around 100 degrees and your 20% comes in around 100 and 40 degrees, that's a pretty good setup there for channel 1. You just want to make sure that when you scroll into that 100%er that it starts down and to the right, which it does. If it starts up and to the left, that means you have your rotation 180 degrees out. Now what I'm going to do is flip through the channels. I'm going to go to channel 3 next. You can see that I've set that one roughly the same. But when I've let's see here. When I measure, let's see. I got to find the button in the dark here. And when I scroll up to the 60% flat bottom hole, wow, and that's less than 90 degrees. On channel 1, which was a higher frequency, that signal was about 110 degrees. So there's less phase lag for the deeper flaw. Why is that? Well, because lower frequencies penetrate through the material quicker. Okay. Let's go up to the 20s. The phase lag on channel 1, which is 400 kilohertz, was probably 20, 30 degrees more phase spread than this. This one, there's less phase lag because the lower frequency, 200 kilohertz, penetrates quicker through the material, or the eddy currents do. So in this vein, let's go to channel 5, even less phase lag. We'll go back to the 100. Still, it's set to about 40, but the phase spread between the 100, which is right there, and the 20s, that's only like, 40 degrees of phase spread. Now, the reason that we run these different frequencies, well, there's quite a few reasons, actually, but I'm going to hit a couple of the main ones. When you get out your slide rule calculator and you determine that your material is Inconel 600, for example, in this case, and the conductivity is 1.6% IAX, you can dial those number, and the wall thickness of 50 mils, 0.050 inches. You can dial those values into your Cal standard, and what that's going to give you for an F90 frequency is about 180 kilohertz. What 180 kilohertz does is it achieves about 90 degrees phase spread between shallow ID and shallow OD flaws. So for this configuration, I didn't run 180, I'm running 200. But that also sets about 90 degrees, maybe a little more, maybe a little less, between shallow IDs and ODs. That way, when you have flaws that are originating from the OD, which in many cases they do with tubing, even shallow flaws will be sticking pretty much straight up and down on your Lysigue screen, so they're easily detectable. And if the signal has quite a bit of vertical displacement on your Lysigue, and you have the corresponding channels strip chart set to vertical, you're going to be seeing the vertical component kick out a lot on the strip charts like you do on the left-hand strip chart here, which is synonymous with that Lysigue channel. See how that one's got a lot of vertical displacement? Sticks out well on the strip chart. If it's going straight up and down, it'll stick out even better on the strip chart. Okay, so now that we're parked on the let's see, let's go back. Gotta find the button in the dark. We're gonna go on the 100% hole right there. And we're just gonna step through all the frequencies. Okay, there's 1, 3, 5. They're all set to 40 degrees. The spans are a little bit different, but that's okay for this demonstration. Now we go to the absolute channels, 2, 4, and 6. So typically you would set these also to 40 degrees. But remember, this signal, it's a differential arrangement that's causing the signal, but the signal that we display here looks more like an absolute. But that's actually comparing a reference standard to your test coil and the actual tube that's being tested. So it's comparing the two, but it gives you an absolute type signal. And when we configure it this way, if you have a long gradual wear, for example, in your tube, you'll get a long gradual shift or drift on an absolute strip chart. Differential arrangements, which were channels 1, 3, and 5, those are better for short flaws like short axial cracks, short pits, because it's comparing one area of the material to the other simultaneously, okay? Now, let's go to channel 2. Now, this is probably set to like 35 degrees. Some procedures will have you set the 100% hold to 40. Some will have you set horizontal noise, which is a small component here, to set that horizontal. That will give you clean strip charts and better detectability for flaws when you set noise horizontal. Channel 4, channel 6, they're roughly 35, 40 degrees. Now, channel 7 and 8 are pretty low. They're about 1/10 of what our channel 1 is. And a lot of times, this is actually the 100% hole on both channels. Span's pretty weak on that one. But what they'll typically do for channel 7 and 8, which are your low frequencies, they will set those on the tube support plate, which is right about there. So now if I flip over to channel 1, you can see how that's blown way off the screen, because the tube support plate is a big chunk of carbon steel on the outside of the tube that's holding the tube in place. Heat exchangers will have many tube supports, layered throughout the component, and when you assemble the heat exchangers, your tubes will be fed through each one of those holes, and they'll come out on the other end through the opposite side tube sheet. So those tube support plates are good. They're meant for a purpose to hold the tubes in place, but they can also cause problems like wear fretting in the tube from rubbing against the tube wall. That being said, a tube support plate's a big piece of metal. It's conductive, and they will affect the eddy currents from your coil that caused by your coil a lot. So for channel 7 and 8, we usually set the TSP, or the tube support plate signal. And how we would set that is like this. We are going to bring that span down to about 50%. And then we rotate it around something like that. Again, your procedures will tell you how to set all of these spans and rotations. But if you're a level 3 and you're developing a test, you figure it out. Look at some old procedures, look up your code requirements, and come up with the best set of solutions. That's your absolute signal. We call it Joe's nose. Joe's looking to the left. That's the way you rotate that channel. And I think I put a mix in here. let's go look. I constructed a 2-channel mix. So what that does is it mixes out your tube support plate. So notice my data window. Let's see, find the buttons in the dark again. One moment, please. Yeah, so if you look at my window on the strip charts here, I'm parked right on top of that tube support plate signal. But if you look in the listed view, all I see is a little bit of probe wobble noise. That's because the tube support plate signal has been mixed out on this channel. So if I go switch over to like my mix 1 strip chart right here, you'll notice that the tube support plate signal, while visible on channel 1 strip chart, it's been mixed out on the mix. However, if I now move my cursor down to the 100%er, look at that huge signal on my mix. The mix was successful because it retained signals from the flaws that I care about, the 100, the 60, and the 20, and all flaws in between, but it mixed out the influence of the TSP, which is right here. That way, when you go to a real heat exchanger tube and you got a bunch of big support plate signals, you just flip over to your mix channel and you can see the tiny flaws that may have been otherwise masked behind an unmixed channel. Okay, now that we discussed about the setup a little bit, let's talk about the phase spread. So here is going to be channel 1. My span is extremely huge. Let me crank that down a little bit. But what I want to do for the phase spread on this is, I guess I'll just step through them real quick here. So the 100%er looks the same on all of the channels. Channel 1, channel 3, channel 5, they're all set to 40 degrees. Now the reason they're all at 40 degrees is because I set them to 40 degrees, okay? That was done on purpose. But when I leave it set to 40 degrees on channel 1, 3, and 5, we watch what happens when we pull the probe past the 60%er, which is a little bit farther away before the eddy currents see anything happening. Notice how that phase is increased, okay? And then we go to the 20s and it's even more. So I'm going to open up this window a little bit here so you can see all 3 of those at once. Okay, I got to do a little minor adjustment here. Hold on, there we go. Okay, now that I've got the window open so you can see all 3 flaws at once, watch what happens when we go to channel 3. The 100%er is still at 40 degrees. There's channel 100 at 40. There's channel 300 at 40. But if you look at where the 20% flaw is, which is about 130 or 140 degrees, that's channel 1, quite a bit of phase lag. And when you go to channel 3, a lot less phase lag. What do you think is going to happen when we go to channel 5, which is even a lower frequency? Even less phase lag. So channel 1 is said to have a large phase spread between the 100% flaw and the 20% holes. For the 20%er, there's actually 4 flat bottom holes 90 degrees apart around the tube at the same axial location in the tube. And the reason they put 4 is because they're so shallow. To give the signal amplitude that we need to perform a proper calibration, they need to make 4 of them. Now, since they happen at the same axial location within the tube, and a bobbin probe averages the entire circumference of the tube and gives you 1 signal output, you get 1 signal even though there's 4 flaws there. If you wanted to see that in your eddy current data that there was 4, you'd either have to use a rotating probe or an array probe because they have 360 degree resolving capability around the tube circumference. Okay, so we use F90, which is this channel, for detection because most of the flaws will stick straight up if they're shallow ODs. If you want to size those flaws, ASME code requires that you use a channel that gives you more phase spread. Many of the code years say when you set your 100% hole to 40 degrees, the signal from your 20% flaws has to be between 50 and 120 degrees more phase, like from the 40 degrees from your 100%er. So what that's saying is, hey, on this channel 3 that you're looking at, there's not a lot of phase spread in there to accurately size flaws, from 100% all the way down to 1%. That's 100, 99%, 88%, 87%, 85, 70, 60. There's a lot of percentages between 40 degrees and 180 degrees. But if you use a channel that has low phase spread like this, every degree of phase angle shift, you're going to have, 2 to 3 percentage points difference. So to have a more accurate sizing curve, you got to use a frequency like this. And this meets that ASME code requirement of having, substantial phase difference between your 100% hole and your 420s. In this particular case, it looks like there's about 90 degrees between the 100 and the 20s, not to be confused with the 90 degree spread between shallow IDs and shallow ODs, which the F90 frequency will give you. Now, what does this look like on our analysis curves? This is a curve that I constructed earlier for channel 1, and this is how the instrument correlates phase angle of a signal to depth. I went in here and I told this particular software feature that a 40 degree signal was set to 100 degrees, and then I scrolled to my 60% flaw signal. I noticed I was 87 degrees, so I punched that into this program here. And then I went and navigated to the 20% signal, which had a lot of phase lag on channel 1. I plugged in 140 degrees, set that to 20%, and drew this curve. Now you can manually adjust these numbers. If the 20% signal was actually at a little bit farther out, I can dial that in here and it'll stretch the curve out. But you always want to use as-built dimensions when you're making curves. I think it was at 144 degrees, so we just left it right there. Now, what happens if you go to channel 3? I don't think I made a curve here yet, so maybe we'll draw one. I'm going to go to analysis curves. Yeah, that's not right. So the 100% is at 40 degrees. Let's see here. So for this case, we're going to make our window a little bit smaller. Because the 100's at 40, I know that that's good. I go to my 60% flaw, which is right there. And I'm going to measure that angle, but I'm going to use max rate. Max rate actually it's the maximum rate of change. And you're going down, and then you got this long flyback angle here. That's the maximum rate of change, or max rate, and that's the angle that we're choosing here. So that's 118 degrees almost. So we go into our analysis curve. The 100's already at 40 degrees. Now what did I say that was? 118 degrees. So in here, we're just going to use the hula button, and we'll go down to 0.2. I have a short memory. I think it was 118 degrees. Set it to 118. 60% is good. If our as-built calibration standard number was 59, we use 59. But for this demonstration, 60 is good. I'm going to go back to the data. I'm going to rotate to navigate to the signal from the 420% holes, flat bottom holes. I'm going to measure that using max rate. That's 120 degrees. So go to the analysis curve. I'll go down to here. Okay, I can already see I screwed something up here. That's 120, we said. Now this curve's going to come out all jacked up because I messed up on the angle of the 60. So I'm going to watch this. A lot of back and forth, a lot of trial and error with eddy current. You're going to hear that a lot. There's a lot of times you have to play around with it to get it right. But you'll know in the end because you have to check your setup. Okay, so here I'm back on the measure. I'm going to hit the max rate. Oh, I was looking at the volts. See, I said 118 degrees, 117 volts. It's actually 73 degrees. See how we can tell when we make mistakes? 73 degrees. So for the 60, I'm going to go here and I'm going to set that to 73. And you're going to watch that curve redraw itself. And in the end, it's going to look absolutely perfect. There you go. So what I would like to do is go back into that, and hopefully I can go up to the, oh yeah, channel. That's what I want to do right there. Okay, that's the curve for channel 1. Now remember, channel 1 had the most phase spread. Look at how wide the curve is. 100% is 40 degrees, go straight down to the, so it's angle, it's a phase on the bottom and then percent through all on the left. So you just look at 40 degrees, follow it up, 100% flaw. Based on our calibration, if you got something about 85 degrees, go straight up on here, it's 60%. If you got something about 145 degrees, go up to the curve, it's about 20-25%. Now watch what happens when we go to, so this is channel 3. Go to channel 1, it's hold on. All right, another mistake made by Mr. Ed. Let's see here. Channel 1, channel 3. Oh, it did have a little bit of collapse. Okay, that's good. Just confused there for a minute. So this one's got quite a bit of phase spread. Okay, scratch all that. I was expecting this channel up here to be changing. This is actually showing us the curves for the different channels, but I was looking for this to change. And that's not going to change because here I'm looking at the calibration curves, not looking at the raw data. So that's okay. So you can erase about those last 2 minutes from your mind. Okay, channel 1, the 420s are at about 145 degrees. And if you go to channel 3, those same flaws are at about 120 degrees. Now let's go to channel 5. I probably don't have a curve set up. Yeah, when I went to channel 5, you see 4, 5, 6, they all look exactly the same. So I didn't set one up for 5 yet. So we'll do that real quick. So here, okay, that's the channel 5. Our 100 is set to 40 already, I know that. This is going to be the hole from our 60%er. So for there, we're going to hit the max rate. Gives us 73 degrees. So I'm going to go into the curves. And then for the 60% or 73 degrees. So because I clicked on that max rate button, it actually took that number over here and set it automatically. So that's a little quicker. And then when I go up to the 420s, which is right there, and then I hit the max rate button and then go to analysis curves. See 101 degrees. I didn't put it in there. All right. I thought that was automatic. Doesn't matter. What did I say was 111? No, 101. 101 degrees. So we're going to take that baby down to 101 degrees. Again, use the as-built dimensions. If that was 22%, we'd dial in 22. But for this, we'll keep it 116, 20. So now let's go into the curves, and then we'll go back to channel 1. Most phase spread works really good for sizing OD flaws because there's a lot of different phase angles to choose from, and each phase angle has a different depth. Then when I switch over to channel 3, you're going to have less phase spread, so your sizing resolution capabilities decreased a little bit. When I go to channel 5, oh, why didn't that work? Okay. Don't you like how we get to redo things here? For some reason, it didn't stick. Okay, 1, 3, 5. For some reason, it didn't stick. So we're going to try this one again. Notice how we like the trial and error. 100. That's the 60. I'm going to hit max rate. Analysis curves. That's the one I want. Okay, now we're going to go to this 20s. We're going to hit max rate. We're going to go to 78 degrees. We're going to crank that down to 78 degrees. All right, I got something messed up again. Let's start from scratch. Here we've got the 100% at 40 degrees. That looks good. Then we're going to go to the 60, which is right there. Max rate, that's going to be 59 degrees. Oh, I put 59%. See how I did that? What we need to put in is 59 degrees. Now that we got 59 degrees and 60%, it's starting to look better, right? Okay, and then finally, we're going to go to the 20s, which are right there. We're going to hit max rate. 78 degrees, so we'll go here. And we're going to change this to 78 degrees. And 20%, that looks great. That's B-E-A, beautiful, as Jim Carrey says. So now look at these curves that we got them drawn. 100, most phase spread. Actually, that's 400 kilohertz. Then you go to 200 kilohertz, less phase spread. Then you go to 100 kilohertz, it's got the least phase spread, but it's the most penetrating. So now you've seen a lot about phase spread. I'm going to try one last thing for you here to sort of put a bow on it all. I'm going to go and select all of the various frequencies at the same time so you can see them all at once. And these are all the differential channels. So now I'm going to go to measure. I'm going to go down here. All right, there's TSP on all the channels. Let me crank my window size up a little bit just to give you a little better. Okay. Yeah, we've got some those signals at the other end of the standard are actually wear scars, so they're a bit wider. Then you have a non-flawed TSP right there on all the channels. And then I go a little bit further below. That's when you get the Cal standard flaws on the various frequencies. So a lot of phase spread on channel 1, 400 kilohertz. Less phase spread on channel 3, 200 kilohertz. That's the F90 frequency, best used for detection. The green here, that's the high frequency, best used for sizing. The purple data here is 100 kilohertz. That's used for creating mixes, confirmation channel. And then channel 7, that's usually used for a locating channel to help you figure out where you're at along the length of the tube. So that's a lot about phase spread, and we got to make some analysis curves and see how the phase spread is very apparent for sizing curves based on phase. Leave a comment, leave a question in the comments. If there's another type of video you'd like to see, just comment below. And if you find these videos useful, please consider liking the video, commenting, and subscribing. That'll help me build some followers and encourage me to keep on making videos for you all. All right, have a nice day.